Everybody, good morning and welcome to today's Ansys Virtual Academy, where we will be covering how to mesh dirty CAD using the Fluent Mesher. My name is John Dow. I'm your host today, and I'd like to introduce you to Snehita Sakar, our CFD applications engineer. She's going to be walking you through what is a dirty CAD, how to mesh it, and what does this all mean to you in your workflow. Snehita, please take it away.
Thank you so much, JD. Can you guys hear me?
Yes, loud and clear.
Awesome. Good morning, everyone. My name is Snehita Sarkar. As JD mentioned, I am the CFD application engineer here at CAD, and welcome all of you for today's ABA session. Very excited to share with you the topic. But before I delve into the actual presentation, just a reminder that if at any point you have any questions, queries, if something is unclear, you can put down the comment or question in the Q&A box on your screens, and we will get to it towards the end of the presentation. Also, towards the end, if you could take a minute to fill out the survey, that would be really nice. We look forward to your recommendations and feedback and try to incorporate it in our future ABAs. With that said, let's jump into the topic right away. So I'll go over the agenda just to introduce it, and then we'll look into the basics of what we're trying to do here. So today I'm going to be introducing to you Ansys's mesh wrapping technology that we use for meshing dirty CAD geometries. This meshing technology in Ansys Fluent is called fault-tolerant meshing workflow, which is why I've used the acronym FTM. After introducing some basic concepts related to wrapping and FTM, I will move on to do two demonstrations. In the first case, I'll demonstrate the generation of a fault-tolerant mesh for internal flow purposes. And in the second one, I'm going to generate a fault-tolerant mesh for external flow. Now, to begin with, let's talk about what fault-tolerant meshing means. Now, fault-tolerant meshing is the meshing workflow that you would use within Ansys Fluent if you were to mesh a dirty CAD or geometry, right? So this is a feature that is available within Ansys Fluent. Now, what does fault-tolerant meshing actually do, right? Now, suppose you have a dirty geometry. We as engineers often encounter such geometries in which there are gaps, holes, intersecting surfaces. And usually, if we have to prep these geometries for a CFD simulation, we have to go in, clean it up, make sure that it's watertight so that we can extract the fluid domain, right? Now, in some cases, it is easy because the geometry is simple enough, but there are other cases wherein the geometry gets complicated, there are minute features, you have to go into each nook and cranny, becomes tedious. You might not have the time or the personnel to go through these steps again and again. In that case, wouldn't it be great if you could completely bypass this step and directly go from an unclean geometry to a CFD mesh? Well, fault-tolerant meshing allows you to do exactly that, wherein you go from a dirty CAD geometry to a CFD mesh and generate a high-quality, efficient mesh while doing that. Now, what does the FTM workflow within Fluent let you do? It allows you to extract the fluid region through the concept of wrapping. And I will talk a little bit more about wrapping in the following slides and also while doing the demonstration so that you understand how it works. What it does is it wraps over these small faulty features, these gaps, these holes that we want to ignore, that we want to cover, but we don't have the time to do that manually. It also lets you patch a leakage area. If there is a large leakage area in your flow that you don't have the time to fix in the CAD file, then you can use the Fluent fault-tolerant meshing workflow to do that. And lastly, it will allow you to improve your surface and volume mesh behind the scenes with requiring a very minimal input from the user. So even if you're not a CFD expert, if you don't know how to go about improving the mesh quality, Fluent takes care of that for you.
Wow, Snehita, that sounds like it's going to save a lot of time. Setting it up front like that.
Yes, absolutely. That's the idea. So I'm going to talk a little bit more about the wrapping technology. And that's going to be key in understanding how Fluent does this job. On the right hand, you can see two images. On the top, you have a bag around which you have a tight shrink wrap. And here at the bottom, you have another picture about which I'll talk in just a minute. Suppose, for example, this bag, this suitcase is the geometry that you're working with, but it is dirty in terms of having holes, missing faces, gaps, and you don't want to spend the time to fix it manually. What do? You shrink wrap a surface mesh around it. What that does is it patches the holes, patches the gaps, so that fluid does not leak either from inside to outside or vice versa. Now, this is an external wrap wherein you are wrapping something over or outside the geometry. What if you wanted to wrap the geometry from within? That is explained in the second case over here, which is similar to what you would see in blow molding, right? So you basically inject a fluid which occupies the domain inside, and this covers any leakages or patches through which flow could go in from outside or vice versa again. Now, an important thing to remember about this wrapping technology is that even though the mesh that is generated tightly conforms to the external or internal geometry, sometimes because of the local sizing function of the mesh generated, you could glance over tiny features. For example, there's a protrusion, but the mesh size is too big or too small for it, then it might be glanced over while generating the mesh. Now you have to decide as a user whether that feature was important to retain. If not, then you can just go ahead with the mesh that is generated using FDM and then proceed to do your CFD simulation. If it is an important feature that you would like to capture in your flow domain, then you will have to adjust the sizing accordingly so that it doesn't get overlooked. To explain the concept of size function and also the basics of how the mesh wrapping technology works behind the scenes, I have over here on the right an image. Suppose you import a geometry inside the fault-tolerant meshing workflow. This geometry is comprised of outlines that are depicted in white, black, and green. Now you can see this geometry is not perfect. Why? Because it has gaps between the white and black line over here and also over here. So this is an unclean, dirty CAD that we've imported. How does Fluent tackle mesh wrapping around this geometry? What it does is it creates an underlying background Cartesian grid, as you can see in the white cells over here. Now, this grid is not arbitrary. It is generated based on the size function that either we select or Fluent decides based on the geometry imported. What happens is that the geometry that you import is made to intersect with this underlying Cartesian grid. Anywhere where the lines intersect with the grid, you have the dark blue cells or the teal cells. This tells Fluent where to generate the wrap. So for example, in the internal geometry over here, where there is a watertight region, where the green circle is completely closed, it determines that the green line and the underlying Cartesian grid are intersecting in all these regions. So it extracts a watertight region from here. Same goes for the external geometry as well. Now keep in mind that there's a leak over here and the adjacent cell, which shows up as an intersecting dark blue cell, is slightly touching both the black line and the white line. Because it is touching the black line and the white line, it shows up as blue, which is an intersecting cell. Now, what if this cell was too small? What if we could fit in an entire square between the black line and the white line without intersection? Well, then it would not be a dark blue cell because it wouldn't be intersecting. In that case, Fluent doesn't know how to cap this region or extract a watertight flow domain from here. If Fluent doesn't know how to do that, flow will either leak out from inside to outside or vice versa. Which is why I talked about the importance of size function. If your gap is, if your size function is smaller than the geometry gap, the mesh will leak. So we want to be careful about the sizing that we choose. There could be another situation in which you do want to capture the gap between two geometry lines. However, your cell sizing is too big, which is why that feature is completely overlooked and patched. Now that gap may be leading your flow from one region to another, and you might want to capture it. But if your cell sizing is too big, you will end up overlooking it. So in both the cases, you need to be careful about how your flow domain is generated. And there's a very easy way of previewing that in Fluent, which I will show in the demo. Another important concept before we do the demonstration is the concept of a material point. Now, because these geometries are unclean and have openings, somebody needs to tell Fluent where the flow domain actually exists. Is it within the confines of these lines? Is it outside the confines of these lines? Basically define whether your problem is an internal flow problem or an external flow problem. In the first case, you will notice that there is a red line that forms inside the geometry. And if we define a material point in this region, then we are dictating that this is an internal flow where the external geometry bounds our computational flow domain. If the same material point were to be selected outside the geometry, and you can see that the red line over here is now outside the geometry, then we know that this is an external flow problem and the flow is basically bypassing this geometry. So this is an important concept again that we will use while doing the demonstration. So with that, I'm going to move on to the demo now. There are some more important concepts that one needs to know about when setting up the FTM workflow. I will talk about it briefly as and when I do the demonstration. But if you need more specific material about those steps, then please do send us an email and I'll be happy to provide you that information. So let me share another tool.
Hey, Snigdha. So we had a question from the audience, and it's what is watertight geometry exactly? Is it a solid body? So I think the question is in terms of visually, what are we seeing? Is it if it was like in a CAD or a 3D inside of our 3D modeler?
Sure, I can explain that. So a watertight geometry, for example, can you guys see my space plane?
Yes.
Okay.
Yep.
So
yes.
For example, I have a random geometry over here. This is an inlet manifold, right? If this geometry were completely clean, I would have a surface over here, and I would have three surfaces at the outlets over there. And this geometry would be completely closed so that we could extract the flow domain without having to do much. So there would be no gaps, no leakages, no holes like this over here, no intersecting surfaces over here. So anything that is clean, ready for preparation for pre-processing for a CFD simulation, wherein the fluid flow domain is not leaking, would be a watertight geometry. So if, for example, you wanted to do an external flow problem, and this was a complete solid, okay, and you build a cuboid around this geometry to represent the bounding box or the ambient conditions, then if the box is completely closed and this is a complete solid, then again, that would be a watertight geometry. So wherever the fluid flow domain is clearly defined without it leaking through gaps or holes or intersecting surfaces, that would qualify as watertight.
So Snigdha, if I had a water basin with an open top, that wouldn't be considered watertight, correct? Because the fluid's being replaced with air, for example.
So even in that case, that would be, for example, if you were to do an open channel flow problem, you would have to create, a bounding box to cover it up. So basically,
Okay.
you have to create a closed domain, no matter the flow being external or being internal.
Awesome. Thanks.
So yeah, so in this case, like I said, this geometry is far from clean. This is not watertight. Had it been watertight, I could have simply gone to prepare and extracted the volume as I have shown in a previous ABA of mine. If you guys are interested in watertight geometry meshing, please go to our Kativ YouTube channel and check that out. Hopefully you find it useful. In this case, this geometry is not clean and I don't want to spend a lot of time cleaning it, okay? So I'm directly going to export this to Fluent Meshing. So right now, this is a space claim file. I'm going to save it in a particular format. So I go to Save As. And in Save As type, I choose FMD, which is FM database. The reason I do that is because I just want to make the transfer process quicker. But with the recent Fluent versions, the geometry import is more flexible, so you can use different formats as well. In options, if you're doing this for the first time, you might want to select fine in the facet resolution. And that is because we're going to be using, a wrapped mesh around this geometry. So we want the resolution to be as fine as possible. So I'm just going to go ahead and select OK. And then I'm going to save this as file 2. I'm going to go ahead and do that. After doing that, I'm going to share the Fluent Meshing window. Let me know when you can see it. John, can you see my Fluent window?
Yes, I can see your Fluent window, Snigdha. And
Okay.
I'm assuming that it's currently loading.
I haven't loaded it yet. Just wanted to confirm that the window is showing. Okay, so I am in the Fluent Meshing workflow GUI, and this is different from the Fluent Solver GUI. Again, I have explained this a little bit more in detail in the watertight geometry ABA. So if you wanted to take a look at that, it might help you just getting familiar with the overall GUI. So right now we're going to use the fault-tolerant meshing workflow. So over here on the left, where you see the drop-down menu for choosing the workflow type, go ahead and choose fault-tolerant meshing. Now, as soon as you choose fault-tolerant meshing, what you will notice on the left here is a series of tasks that have been outlined. Now you can see that these tasks are very intuitive and very easy to follow. What they basically give you is a top to bottom approach of how to proceed with the fault-tolerant meshing and eventually generate the volume mesh. So even new CFD users or new Fluent users will find this very easy and intuitive when they actually try it out. So right now I'm going to go ahead and finish the first task, which basically asks me to import the CAD. So I'm going to go ahead and click on that. It's going to ask me for the CAD file. So I'm going to browse to the location. And I think I saved it as trial 2. So I'm going to go ahead and do that. And I'm going to go ahead and hit load. So we can see that the geometry loads quickly. And then I'm going to go ahead and create one zone per body. This is just creating the zones based on the name selections that we want to assign later on. And then I'm going to go ahead and click on create meshing objects. And I am using 8 cores on my computer, and this is Fluent 2020 R2, in case anybody was curious about the version that I'm using right now. If at any stage, the meshing takes a little bit longer, I might switch to a mesh that has already been created, but rest assured the steps are the same. So I won't be omitting anything. So as I mentioned, the geometry that was dirty gets transported to Fluent as it is. You can see that there's a hole over here that needs to be patched. And there's also an intersecting surface over here without any edge at the intersection. So we would need to take care of that as well. I think this is probably a probe, maybe a pressure probe. So yeah. So let's move on to the second step over here. We have to describe the geometry and the flow. Now this is the first demonstration. So this is a demonstration for internal flow. So I'm going to go ahead and select internal flow through the object. And then it asks me, would you like to create caps? Now, what are caps? Caps are something that I would have to create in order to close the domain, right? So in this case, because everything is open, I will have to create the caps, right? So I'm just going to stick with yes. Do I want to add local refinement? For now, no. Do I have any extra surfaces? No. So I'll just go ahead and describe the geometry and flow. And it asks me to cap the geometry. So this is my inlet and these three are the pressure outlets. So I'm going to go ahead and select the inlet surface that needs to be capped from this drop-down list. These names, inlet, outlet 1, outlet 2, outlet 3, they are coming from space claim. So if you only define the adjacent face to your inlet, that should do the trick. So you don't have to do much in space claim. So you can see as I hover over inlet, the inlet surface gets highlighted in yellow, right? So I'm just going to go ahead and select inlet, and I'll change the name to inlet 1, and I'll go ahead and create a cap. Once I do that, a cap is created and it closes off this part. I can do the same thing for the outlet as well. So I'll just quickly change this to pressure outlet. Let me do that really quick. So as and when the tasks keep getting completed, you will see a green check mark against those tasks. That means they have been completed. So you can see that now my geometry is somewhat watertight. I mean, of course, there are still the holes and the intersection that we have to take care of. But as far as just the regions being capped, we have now covered it up, right? Now, the next step is to identify the region. So let me go ahead and select that. Now, this is where you define the material point that I talked about in these slides. How does Fluent know whether this is an internal flow or an external flow, right? So what I'm going to go ahead and do is I'm going to select the location of the material point that will tell Fluent whether this is internal or external flow, right? So I'm going to go ahead and select main, which is this body over here. And the centroid of this body, centroid of objects, will be the material point. So let me go ahead and select identify region. If I insert a clipping plane over here, you can see that this point over here is highlighted. So as long as it's inside this body, we know this is internal flow. If I wanted to make this external flow, then I would move the location of this point to somewhere over here, right? So I'll go ahead and select identify region. This will be my fluid region. Right. Now, what if I wanted to select the void region? What is a void region? A void region is where your flow should not leak out. So anywhere outside this manifold would be my void region. I don't want flow from inside the geometry to go into the void region. So I will go ahead and change the region type to void, right? And while selecting the point, let me just choose any of the pipes. And when I choose any of the pipes, the centroid is automatically selected as a location outside. So this looks good to me, and I'll go ahead and do identify region. So now I have two regions. One is the fluid one and one is the void one. Fluid is where my computational domain exists. Void is where I don't want my fluid to go, right? Now the next thing is to define the leakage threshold. Now, what is a leakage threshold? This is a concept that I was talking about while mentioning that there might be other things that you need to take care of in your geometry. So let me remove the clipping plane for a second. You can see that there's a hole in this domain. Ideally, if I were to clean this up in space claim, I would go and fill this out. But I didn't have the time to do that. I want to fix it within Fluent itself. How do I do that? I know the dimensions of this hole. Okay, this is, I think, approximately 4 millimeters in diameter. I know this because I've worked with this file earlier. You can, of course, measure your leakages, your gaps in space claim before exporting it out to Fluent. Now, if I wanted to patch this or to cover this, then I want to enter a leakage threshold that is greater than 4 millimeters. That means you're applying a Band-Aid that is bigger than the hole that you want to patch, right? So if I am able to specify that leakage threshold dimension, then that takes care of this particular gap. If you have a lot of gaps and they are comparable in sizes, you could patch multiple leakage areas at once. So that makes it very efficient. So right now I do want to close this gap. So I'm going to switch this to yes. And I am going to change this to 5 millimeters because I think this diameter is 4 millimeters. So anything bigger than that should work. And I am going to simply define the leakage threshold. Okay, so let me see. So the leakage threshold has been defined over here. And then we move on to update region settings. Now, this is a very handy feature in Fluent wherein it lists out all these zones. If you look at the ones that are volume mesh related, then they will show up as either fluid or solid domains. So the fluid region 1 that we created by identifying the material point now shows up as a volume mesh entry, wherein you can choose which type of mesh you want to fill it up with. Right now, the default is selected as a hex core mesh, wherein the domain will be filled with hexahedral cells. You could click on it and you would see other options like tetrahedral cells, poly cells, or polyhex core cells. So this again is a recent feature in Ansys 2020 R2. I think both fluid and solid zones can now use poly and polyhex core meshes. So I'm going to keep it as hex core and not play around with it. And you will also notice that the void region has also been identified. However, there is no volume filling in it. And now I'm just going to go ahead and update the regions. Now, the next part is very important, wherein you choose the sizing of the mesh. I did explain in that one slide why sizing is important and how it can be used to either suppress features or identify features that are important to your domain. So for now, I'm just going to stick with the default values, but if you wanted to change it up, you could go to custom and input your own local sizing for different refinement regions based on the geometry that you are working with. So I'm going to go ahead and choose these options. And then it asks me if I want to generate the surface mesh. Yes, I can define the overall target skewness of the surface mesh and it will adhere to this limit. So I'm going to stick with 0.8. Note that you can also save the surface mesh at this intermediate stage and use it later on. Right now, I'm not going to save the mesh. I'm simply going to go ahead and generate it. What is the preferred CAD format to get a watertight geometry for CNC programming in many CAM softwares? To get a watertight geometry, you could work with any CAD format to generate a watertight geometry. So it's not something that's only specific to Ansys products. So like watertight is a general definition of how you define geometry. So you could start with a step file, an IGS file. Any solid CAD format can be made into a watertight geometry. if you wanted to, use an STL file or a faceted file for fault-tolerant meshing, Fluent allows you to do that as well. So that is another advantage wherein you don't have to convert that STL scanned file into a CAD format and then import it into Fluent meshing. You could directly import that where we do import CAD geometry in the first task. This is taking a little bit of time to generate the surface mesh. So you can see that the gap over here that we had has now been patched, right? And you can see that without doing much to the overall geometry, you get a pretty decent quality surface mesh, right? Now, it asks you if you want to add the boundary layers. I am gonna stick to one for now, just in the interest of saving time, but you could choose as many as you want. I think the recommended amount of prism layers or boundary layers that Fluent recommends is 3. But for now, in the interest of brevity, let's just go with 1. So this will automatically add the boundary layers depending on how you've identified the fluid region. So you don't have to do much because it already pre-selects that the boundary layers are going to grow on walls. So I'm going to simply go ahead and add the boundary layers. And then we eventually move on to the last part wherein we are going to generate the volume mesh. Again, it's very similar to the surface mesh option, wherein you have to dictate a limit for skewness. Here I have dictated 0.96. And I'm just going to go ahead and generate the volume mesh. So this takes a little bit of time, but it's much faster than some of the other tools and softwares out there that will take a lot of time to generate a volume mesh where you're not even sure about the quality or the count. Especially with the newer polyhex core meshing technology, you get the best of both worlds where you don't compromise on the quality, but get the best possible mesh count without having to over-refine regions. So right now, the insert clipping plane option is on. Let me go ahead and insert a clipping plane in Z or Y. So if I draw the cell layer, you can see that based on the selection that we made of hex core meshes, the majority of the interior or the core of the computational domain has been meshed with hexahedral cells. We selected just one prism layer or the boundary layer for the purpose of this demonstration, so you can only see one. However, if you had selected more would show up. And it was like, it took me, 10 minutes to make this mesh without having to clean up anything. And you could simply just export this mesh or even save this workflow in order to use the same settings with some other geometry. So suppose you have another geometry which is very similar to this, but you do not want to go through all these steps again. You could just simply save this workflow and all these settings would be saved. And when you reopen Fluent Meshing again, you could just load the workflow again and change the geometry and reuse the sizing that you specified for this geometry and get your mesh in 2-3 minutes. So now that we've finished the demonstration for the internal flow, let's move on to the demonstration for the external flow.
I think before we move on from this part of the demonstration, we did have a question pertaining to this demonstration. Sure. We have an attendee asking about the when you were doing the caps. Mm-hmm. They're asking if you could describe what large caps are, because they saw a setting on when you were in the section that describes geometry and flow and internal flow. There was a setting that was asking about large caps.
Large caps. I don't see it here, and I don't know that off the top of my head. But
Okay.
what I can do is I can, check on it and revert back to, the attendee who's asked the question for sure.
Sure. Yeah. Okay. We'll contact the attendee directly after
Sure.
this AVA. And another question about the CAD geometries that work with watertight. We have an attendee that uses CAD geometries that are really meant for CAM softwares. Would that work for Ansys?
When you say work for Ansys, do you mean for Fluent meshing or?
Yes. Yes. So they
Yes.
use an XT format file. Would
Uh,
they be able to import that geometry into Ansys and do a watertight geometry or watertight mesh?
I think, give me 1 second. Let me, I can check on
Yeah,
that
from my
really
memory,
quick.
yeah, from my memory, the XT file format is a pair solid, and
It should
Ansys,
work then.
yeah,
Yeah.
Ansys being CAD agnostic, it could definitely import pair solids. I know that for a fact. That's
I
one of the,
understand why the audience member might have a question, because until a few releases ago, for the fault tolerant meshing, not a lot of formats were compatible. I think you could do STL and you could do FMD, but they've changed that now, and now all CAD formats and STL formats are compatible. But I can send them a document that explains in details which all formats are compatible. And yeah, I'll be happy to revert back to them after the AVA.
okay. And then one last question. For the interface here, we're looking at the Fluent meshing interface. It's slightly different from Ansys Fluent, the solver.
Yes.
Are we able to see mesh quality here? That came from our
Yes.
YouTube channel.
So here you get a brief summary of the mesh quality. So usually I look at skewness and the orthogonal quality or the aspect ratio, but you could also just go here and then check quality, and that would give you the same results. What I would recommend is, if you're not particularly looking to use a hex core mesh, use a polyhex core mesh. Why? Because with polyhedral cells, you don't really have to worry so much about skewness. That's the advantage of using polyhedral cells. And in the interior region, where you have hex meshes, your orthogonal quality is going to be good. So if you wanted to not worry about the mesh quality, just go ahead and use polyhex core, which would give you the best conformance to the external geometry and also allow you to retain a good efficient mesh count. So JD, I'll take the questions towards the end because otherwise I'll run out of time. Won't be able to show the external flow case. So I'm directly going to start, another case over here. So let me just go ahead and import the external flow geometry. Or maybe I should have just closed this and started a new one, but let's see. So I'm gonna select this geometry over here. I'm gonna go ahead and click load. Object. And then I'm gonna go ahead and select update, and it'll load the external geometry. So usually I just, cut out the space claim step where you would have to save it as an FMD file. I just directly imported it in here. So what you see over here is an airfoil, a simple airfoil. And this would be an external flow problem. However, you can see that there are some holes in this airfoil, which we definitely don't want. What we also don't want is a gap over here in the trailing edge. We don't want the, flow from outside to leak inside and vice versa, right? So we're going to go ahead and, select the same things again. So we're going to go ahead and select describe geometry and flow. This is an external flow around the object. And you can see that there is no bounding box around this geometry, which I think JD you were talking about earlier. So I would like to add an enclosure. I would like to cap this off. So I select yes. I do not mess with the other default settings. So I'll go ahead and describe geometry and flow. Now, when I select that this is an external geometry and I do want an enclosure around it, Fluent Meshing gives me an option to create it within this very workspace. So I am going to select this as my reference geometry, and it creates this enclosure around it by default. Now I want a little bit more region in the wake area, so I would want to shift this enclosure or grow this enclosure by a little bit. So there are two options of doing that. You can directly just specify the coordinates, or you can specify the bounding box area relative to the object that you selected from the drop-down menu. So for example, I could just simply do this. And you see how the dimensions of the bounding box have changed based on my ratios that I've entered here. Now I would actually want to increase the Y and Z as well, but in the interest of saving time, let me just stick with this domain. This is just for demonstration purposes. This is not a direction on how to do the CFD accurately. I'm sure the CFD engineers would know about this. So I'll just go ahead and create the external flow boundaries. And as soon as I do that, there's a box that gets created, right? So then it asks me to identify the regions, right? So again, I have to choose where is my flow. Is it internal to the geometry or is it external to the geometry? So initially I would want to select the fluid region, right? So I go ahead and select the tunnel. And if I select the tunnel, then the centroid of object is at this point over here, which is outside my geometry. So this works because this is external flow. And I'll go ahead and identify the region. Okay, I'll select this as fluid region 2. Okay, and then I will go ahead and delete this because this is from the previous case. And I'll mark this as updated. Okay, and then after creating the fluid region, I'll have to create a void region to tell Fluent where the flow isn't supposed to go. So I'll go ahead and select the region type as void. And then instead of selecting the tunnel as the object of centroid, I'm going to select this guy over here. When I select this guy over here, you can see that the point is somewhere inside the geometry. So that works in my case. If you wanted to look at the coordinates of this point and move it, you could also do that. So if I click on this view exact coordinates box, it shows you where the point is located right now. And if you wanted to move it left, right, center, top, you could just play with these settings over here. So for this case, I don't need it. I'm just going to go ahead and identify the region. Now define leakage threshold. Because we have these holes over here that we want to cover, I would have to specify a leakage threshold that is bigger than these holes so that it can patch over. So I am going to choose design 4 as the object, and I'm going to put in 48. And remember how I talked about being able to check within Fluent whether or not your flow is leaking out from one domain to another? You could do that by selecting preview leakages. When you do preview leakages, what it lets you do is it lets you check whether your flow is leaking from one domain to another. So for example, if you move this slider over here, you know how the flow looks. The blue part is the part within the domain, and the red part is the part outside the domain. As long as there is no connection between the two and the blue part is separate from red, you know that your leakages are being captured effectively. So I'm going to go ahead and just select define leakage threshold. Just the leakage one. So this part needs to be deleted because this is from the previous geometry. And I'm just going to go ahead and update this task. Then I'm going to go ahead and update the region settings. Again, the fluid region is selected as hex 4. I'm not going to play around with the default here. But let's just go ahead and update the region. And then choose mesh control options. Let's stick to default. And then we'll create the surface mesh. If you wanted to play around with sizing, suppose, for example, I have not selected the correct value for leakage threshold. 48 is either too high or too low. Then I could simply go to add local sizing and create other customized tasks and sizing options so that my geometry is accurately captured. So this takes a little bit of time. But a lot less time than actually going into the geometry and cleaning everything up. So you can see that a decent mesh has been created. If I were to show you the clipping plane over here, you could see. You could add a little bit more resolution near the leading edge and the trailing edge. But because we don't have a lot of time, I don't want to go into that. But if you have questions about sizing, please feel free to reach out. I'll be happy to answer them. And similarly, we can just go ahead and add the boundary layer. And then eventually just generate the volume mesh. And you can see, while this is happening, that all those holes that we had earlier, those have been patched because of the leakage threshold option that I used. Now I knew from my space plane geometry what the size of those holes actually are. So I could specify a number that takes care of all of them at once. That is some investigation that you would have to do on your end. But once you know that number, then it takes care of a lot of faults in your geometry quickly. And you can see over here how the mesh has been generated. And with Fluent meshing, what is an important feature that I wasn't able to showcase in this particular demonstration is that you can also specify regions of refinement using body of influence, wherein, for example, if you wanted to have different regions of refinement to capture the weight correctly, then you could specify different regions, which are called bodies of influence. And then that would take care of the refinement in those regions. So with that, I'm gonna conclude the demonstration. Overall, if I had to recap what we learned today in this ABA session and why and how fault-tolerant meshing can be of use to you, then one, if you're a new CFD user or even an expert, but you want to reduce your overall pre-processing time, you just want to follow some basic tasks that make sense and get a fast, good quality mesh, then using Ansys Fluent meshing, using fault-tolerant meshing can be really useful. If you have a lot of different geometries that are complex, complicated, you don't want to spend the time to defeature them, then again, use fault-tolerant meshing. You can directly use tessellated scan data without having to convert it into solid CAD formats and generate a fault-tolerant mesh. And lastly, with the newer updates in Fluent, both poly and polyhex4 mesh types are available for you to explore and use and generate a great quality mesh. So with that, I conclude today's AVA session. And JD, do you want to talk a little bit about your next AVA while I take a look at the questions? What happened to the gap at the tail of the airfoil? That got closed as well because we selected a leakage threshold of 48 millimeters, which was much bigger than the trailing edge gap. So if I go ahead and show you that.
Oh, Snigdha, you're still sharing that. Okay. That's good.
Yeah.
Yeah, we can see it now.
Basically that area got closed off. Had it not been closed off, then basically the mesh would have penetrated inside. So because we specified the leakage threshold of around 48 millimeters, that not only took care of the holes, that also took care of that trailing edge gap. And if you have animation of flow, could you please show results? I don't have the animation. I'm guessing you're talking about the animation of flow with this airfoil, but I don't have it right now because I didn't really do a simulation. And as it is, this is not the correct mesh for an airfoil. It needs more refinement in the wake region and more boundary layers. So this was just a demonstration to show the meshing capabilities. But within Ansys database, there are a lot of airfoil examples that you could probably find if you do a quick online search. If not, feel free to reach out to me and I'll be happy to help you out. Does Ansys Space Claim have auto clean and healing options? There are certain options. For example, again, I would like to refer to the AVA that I did on watertight geometry meshing, wherein you can use certain options within Space Claim. Let me share Space Claim real quick. Can you guys see Space Claim, Jerry?
Yes, I can see Space Claim.
So there are some options in the prepare section. You can automatically take care of interference. You can take care of bad faces. When you go to repair, you could use stitch, gaps, and missing faces. And it does automatically identify some of those errors in your geometry and fixes it for you. But then again, this is just a simple example case that I'm using. You could probably just fix it really quick within Space Claim and use watertight geometry. And I would do that. In this case, I would do that because this is a pressure manifold. For example, if this were for a charge airline, the pressure is not that high. If it's around 3,000 Pascal or 4,000 Pascal, for a certain kind of engine, then you don't want to use a wrapped mesh around this geometry because it might not be accurate. So you have to decide in which case would you compromise on the exact accuracy of the geometry to get directional answers for your CFD simulations. If your velocity or pressure values are too delicate, too sensitive based on the geometry features, then stick with watertight geometry meshing. If it's something that won't probably vary, if you de-feature a certain edge, then go with fault-tolerant meshing. Any more questions? Is it possible only to import the STL file? Yes. Or also in watertight geometry. I think in watertight geometry, you would need a CAD format, but I can definitely check up on that and get back to you. In watertight geometry, I think you would have to use a CAD format. The STL works for fault-tolerant meshing. But let me double check on that and get back to you. I think I've taken all the questions. JD, do you have any more questions for me?
No, I do not. We could talk about the next AVA session.
Do you want to talk about it, or I could?
Yeah, sure.
Go ahead.
So our next AVA session on September 29th is going to be a structural focused one where I will be going over parameters, what they are and how we can use them. And I'll be doing a quick introduction to Ansys Design Explorer. It's a powerful tool that rapidly lets us know um, what is impacting our design the most in terms of the features that we have modeled. That's going to be on September 29th, 10 a.m. I invite you all to join, and please let your colleagues know, especially your structures colleagues, anybody that's using Ansys Structural today. Thank you.
Oh, I'll be attending it too, JD. Looks really important to our day-to-day workflow. Parametric analysis and optimization is something that all of us could benefit from. So even if you're
Yes.
just doing CFP, please feel free to join that session so that we can look at how Design Explorer works within Ansys.
Thank you all, and please have a nice day.
You as well. Thank you, everybody. Bye-bye.